So the previous slides, we already showed that we can actually write the homography matrix in this form. And then we can easily transfer this to the matrix form as A multiplied by H is equal to 0, which A is equal to that, and the H is just like all of the variables that I have in my H matrix, if you recall. With this H matrix, I have H1 all the way to H9, if you remember that. So this H will be the variable. I have the matrix A, which is this guy, and the A multiplied by H is equal to 0. And we would like to solve that. And we already also mentioned that with the homography matrix, we have 8 degrees of freedom. And if we have 8 degrees of freedom, we need 8 equations. And if we need 8 equations, so 4 points should be sufficient, because each point will give me 2 equations. 2 multiplied by 4 is equal to 8. We put that in the matrix form. This will be like, as an example, point 1. This will be point 2, and so on and so forth, till point n. If I am talking about homography, till point 4 should be enough. If I speak about translation, 1 point will be enough. If I speak about affine, 3 points will be enough, and so on and so forth. I may also take more points than what I really need, yes, because this will be like an over-determined system, and we need to solve A of H is equal to 0, and we mentioned that we need to do that by something called SVD. So we need to solve that by singular value decomposition. So A of H is equal to 0. This is our target, and this is called homogeneous linear least squares problems. We have already explained how to solve A of H equal to B, which is called inhomogeneous linear least square problem, by just using the pseudo inverse of the matrix A. But this will not be possible with using to solve A of H is equal to 0. Instead of that, we will use the singular value decomposition to solve for H. So what is singular value decomposition? Meaning that A can be decomposed to 3 matrices or to 3 stuff. These 3 stuffs is called U, sigma, V transpose. What is U? U is a matrix. So you can think of this. You can think U1, U2, U3, of course, column-wise. How about V transpose? Again, also orthogonal matrix, but since it is transpose, so this would be V1 like that, transpose, V2 transpose, till Vn transpose like that. So why we didn't use, for example, eigenvalue decomposition to solve it like that? Because if you recall from eigenvalue decomposition, that is something exactly the same. However, I have V sigma V transpose, or U sigma U transpose, meaning that this matrix is the same exactly as this matrix with the eigenvalue decomposition, correct? But usually, in this case, I have to have a square matrix. But singular value decomposition will be a little bit more general with even a rectangle matrix. And that's why you can see like U might be fat and V might be thin, or the other way around, if you recall. Okay? What is sigma? Sigma will be a matrix that basically you will have the singular values, and these singular values will be in a decreased order. In this case, since I have 9 of these H, 9 unknowns, I will have till sigma 9. Sigma 1 will be the largest, sigma 9 will be the smallest. And going from all the way to sigma 1 to sigma 9, I'm just decreasing order. So it is ordered in a decreasing order. And also you can write actually A in this form as the summation of the sigma multiplied by UIs and then VIs transpose, which is exactly the same thing. Okay, what else, or how we can take this to solve that particular problem? Let's spend some time just like to remind you some of the nice features of this sigma value decomposition. So if we take A is equal, as we mentioned, U sigma V transpose. Suppose that I would like to multiply this matrix, this equation, by A transpose from the left. So if I multiply with the left to the left-hand side, I have also to multiply with the left to the right-hand side. What is A transpose? A transpose meaning this basically transpose. So we will just substitute A transpose A, it is U sigma V transpose, all transpose, multiplied by U sigma V transpose. This is will be not but V sigma transpose, and then U transpose, and then this is just U sigma V transpose. So A transpose A is equal to that. If you see this, U transpose U is equal identity. Why? Because this is just orthogonal matrices. And we mentioned earlier that U minus 1 is the same as UT. U transpose is the same as U to the power of -1, or the inverse, since this is orthogonal or orthonormal matrices. So at the end, you will have V sigma transpose sigma, V transpose A transpose A. You can call this like another symbol like that. Does that remind you of something? This is just the eigenvalue decomposition. And this basically will be the eigenvalues, and the V will be the eigenvector to a new matrix called B, which is A transpose A, because A transpose A will give me a square matrix. So now V is the eigenvectors of A transpose A. The same, by the way, I can get if I multiply A by A transpose, I will end up with having U will be the eigenvectors for A transpose. Okay, so now V will be the eigenvectors for A transpose A, and this guy will be my new lambda, which is basically, you can think of this as a sigma square. So this will be sigma square. So I now have a lambda square, or the eigenvalues is equal to sigma square, and my eigenvector is equal to V. So you can think of this, as we mentioned earlier, that this guy will be the stretch factor. This guy is just rotation, correct? So I rotate, stretch, rotate. And this will be also the same things as we map that when we have only two eigenvalues, lambda 1 and lambda 2. We already mapped that to the ellipse, correct? We map that to the ellipse. One direction will be the lambda 1 or eigenvalue with a stretched lambda 1, and the other eigenvalue stretched lambda 2, or actually 1 over square root of lambda 2. And same with the other one, 1 over square root of lambda 1. The same can apply by the signal value decomposition. So you can think of this U sigma V transpose also again as a rotation, but just different rotation. You rotate by V transpose, and then you stretch, and then you rotate by another U. This is just like intuition of behinding that. Okay, so again, why you are telling me like V is equal to V is the eigenvalues of A transpose A and so on and so forth. Why is this basically important? Because I would like to solve A H equal to 0. And if you recall, when we mentioned A H equal to B, we said like we would like to minimize the difference, A H minus B norm square, correct? Earlier, what we had that we would like to minimize A H and then minus B this square. But B here is 0, so we don't have here the B, correct? What I need to do instead is just like minimize this A of H square, correct? The norm of A of H square. This is what I would like to minimize, correct? But if you look at this, I'm asking you, what is the solution of A of H equal to 0? You might say that H equal to 0 is a solution. Because if I multiply A by 0, it will give me 0, correct? But this is not an interesting solution that we are searching for, correct? But when I do the minimization, I might get like H equal to 0. It's not only that. The scaling factor of H might give you a solution. So let's say like I found H. 5H is still a solution, 6H is still a solution, and so on and so forth, correct? So how then to solve this correctly? I can solve this correctly by minimizing this value, subject to, I would like to put some constraint on my H because I don't want the solution to be equal to 0, and I don't want to get like a scaled value of H, just like subject to that this H is basically equal to 1. So if I have that, then I can begin to solve that particular problem. Or even H squared is equal to 1. This will not be like the big stuff. So minimize A of H squared subject to H transpose H is equal to 1. So now the magnitude of H will not exceed 1. How to solve something like that? There is like different ways that we can do that. One of the things is called the Lagrangian multiplier. It's called the Lagrangian multiplier of this H. Is not but this guy, which is my objective function, what I would like to minimize, which will give me at the end H transpose A transpose AH minus my constraint. My constraint is what? This. So minus my constraint H transpose H, but I have to use what we call a constant or a Lagrangian multiplier, let's say lambda. Lambda is not the singular values, yes, or the eigenvalues, just lambda is the Lagrangian multiplier. We'll show you later on what is the relation when we solve the problem, but that's just for now. This is how we should solve an optimization problem, by the way. Okay, so I have now the Lagrangian multiplier is equal to this, which is my objective function. If you were like to decompose A of H norm squared, it is just like H transpose A transpose multiplied by A H. Derive this, so derive or derivative with respect to H, and then equal to 0. When we do that, you will find at the end that A transpose A H minus lambda H is equal to 0. So at the end, A transpose A H is basically equal to lambda H. Did this remind you of something? A matrix multiplied by a vector equal a constant multiplied by the same vector. Yes, eigenvalue decomposition, correct? So A transpose A, this is what we call it here B. And here the lambda is the eigenvalues. And the H will be the eigenvectors. But what is the relation between this H and this V? It's the same, yes? Because H is the eigenvectors according to this equation to A transpose A. And I already showed you here that V is the eigenvectors or also the same exact matrix A transpose A. So basically the solution of H basically V. So if I go to V and get the solution of these eigenvectors, I should be able to solve for H. But the next question is, which eigenvector I should take it from that V? I should take the one that is corresponding to the 0 eigenvalue. I should take the one that is corresponding to the 0 eigenvalue, which I'm expecting the 0 eigenvalue will be the last sigma, because I told you it will be in order, correct? It will be in order, sigma 1, higher value, sigma 2, lower, sigma 3, lower, and so on and so forth. I have to go to sigma 9, yes? Because I need to get the lowest. I need to solve for AH equal to 0. So I need to get the eigenvector that is corresponding to the eigenvalue equal to 0. But in the practical case, the lowest sigma or the lowest eigenvalues will not be equal to 0. It will be something very close to 0. And that's why, accordingly, I will take the V, or the eigenvector column, that is corresponding to the smallest eigenvalue. Because in practical, I will not get a singular value that is equal to 0 in this case, since I have a noise. So since I have a noise, this sigma will be perturbed a little bit. So it will have some very, very small value. Let's take the eigenvector that is corresponding to this small eigenvalue. And if I take that, this will be the solution. So let's see what I already mentioned again. So with this, we will have the singular value, as I mentioned, from sigma 1 all the way to sigma 9. Ideally, this sigma 9 will be equal to 0, because now I have a couple of cases. If sigma 9 is equal to 0, so I'll just take the eigenvector that's corresponding to the only 0 eigenvalue, or to the 0 eigenvalue. But in the real situation, sigma 9 will not be equal to 0, because I will have some noise. So I would agree with the smallest one. So sigma 9, it will not be 0, but it will be perturbed a little bit. And in this case, it will be a little bit greater than 0. And I will take the eigenvalue the eigenvector corresponding to this sigma 9. We will not handle the case, as I mentioned earlier, to have like a homography being undetermined. We'll not solve for that. But for now, we will take the column in V, or the eigenvector in V, that is corresponding to the smallest eigenvalue. After that, I have the H, because now the H will be that particular, the solution of H, H1 to all of H9, it will be just one vector of this particular V matrix. So now I have the H. Next, what I should do. If you recall from previous slides that I told you that P prime is equal to HP. This P, if you recall, in the homogeneous domain, this P dash in the homogeneous domain, and I need H. I would like to get this H. And if you recall again that H is equal to H1, H2, H3, all the way till H9. Now I solve for H, so I have the vector H like that, H1, H2, all the way till H9. What I should do next? Plug these values here by rearrangement. Yes, put that in this form. After that, plug it here. You already have the P, then you'll be able to get the P prime. Because ultimately, what I need is to get a translation. I would like to know how I can translate P dash to P, or P to B dash. Because I would like to blend the two images together, if you remember, for the panorama. I would like to stitch them together. And when I would like to stitch them together, just like concatenating them will not work as we showed last time. We have to do this a little bit carefully. And we said that we will use homography as an example, or any translation that I would choose. But we just choose the one with the highest dimension that we have from our option. Why? Because this will give me a lot of flexibility. So if I have a point and I rotate, translate, stretch, and all of these kind of things, I should be able to capture that from the homography, because the homography will allow of all of these changes. If I just choose from the very beginning, instead of H, to get another matrix called T, and this is T is for translation, so I'm expecting that only translation happen, a movement in the X and a movement in the Y. Then I have, if I assume that this is the situation, I should just need 1 point. And from this 1 point correspondence, I should be able to tell you what is the matrix T, if I have assumed that transformation is only translation. But just to be safe, from the very beginning, you have to assume the most difficulty. Yes, the highest thing that you have done to your image. And if I didn't do all of these kind of things, I am expecting that part of this H will be 0. Because for instance, I have done only translation. So 2 of these variables will be basically the translation, and all of the other values will be zeros. Correct? Because this is what really happened, but I have assumed something even more. But then I have been able to capture that, and so on and so forth. Colleague, look at this, the problem differently. Again, as we already mentioned, minimize the A of H subject to the H square. You can just like take the function, derive the function at the end. This is what you will get again. H is the eigenvector of these matrices, and since equal to 0, I have to take the eigenvector that's corresponding to the 0 eigenvalue. But we mentioned that is not practical to have a 0 eigenvalue in this case. I will take the one with the smallest eigenvalue since I have noise. So we can solve with these two different ways, either by U sigma V transpose or by A transpose A. Both of them will give you the same thing. So now back to remind you, like when we stitch together a panorama, we take sequence of images from the same exact position, rotate the camera. We have the camera like that, just like take the image from this, and then take the image, and then take the image, and so on and so forth. So I'm just rotating the camera. So now I have all of these images, and I would like to build my panorama. Whatever we are doing right now is just to help building the panorama. So we took the sequence, we finished this. Second thing is compute the homography. We also finished this. So now I have the translation. I know what is H. I know how to translate one image to the other image. Or what is the transformation matrix. Then what I should do. Transform. Because I already would like to stitch them together, but with the more information from that particular matrix H. Just do the transformation. Transform the second image to overlap with the first, or take the first to overlap with the second. It doesn't matter. It's just like blend of the two together to create a mosaic or a panorama. If there is more image, just repeat the same things. Repeat the same things. And then get the H, transform, blend, and so on and so forth. But what will happen when I transform the second image to the first image or vice versa? So I may take this to this, which we call it like forward warping, or I may take this to this. We would like to study each of them and understand what is the pros and cons for each method. So now, just like again, I would like to take one image to transfer to the other image so they can blend it together. I can create the panorama at the end. So now I have, for instance, enough pixel to pixel correspondence between the two images, solve for the linear transformation as before, and then get H. Then any transformation from this X, and this is X dash for instance, it is just X multiplied by H, it will give me X dash, correct? Another point here multiplied by H, it will give me another point here, and so on and so forth. So I need to do that. I need to take the X's, the corresponding X's that I got, multiplied by H, get the corresponding point there. Okay. If there is any problem with this procedure? The problem when I do this, that unfortunately, if you remember, I have to discretize any image, correct? What will happen if this point in my discretization map to a point that is in between? How I should allocate the values for these 4 points? Because this is at the end of my discretization, correct? The image will be just discretized with pixels. And according to my resolution, I have to specify these pixels. Assume that after this translation, it is mapped to something in between the pixels. How I can get this? This is my image. If you go to solve that with MATLAB, you have to discretize the image, correct? Each one of these, I am expecting should map to each one of these. But after you do the transformation, unfortunately, this is mapped to something in between here. If it is mapping something in between, how I can specify these 4 corners? How I can do this? Fortunately, it's so difficult because this is just like splat the values, yes? I have one value which needs to be splatted like to 4 places. How I can do that? I can say like maybe I will just divide by 4 or whatever the thing is. Okay, so then if I have like another point here that having the same. So then I split this here and then this will be the average and so on and so forth. I can do that, but it will not be like as good as I want. Is this clear? So this is just like distribute the color splitting as we mentioned, that if we have like receive intensity from more than one pixel, just we average their intensity contribution. We can think of this problem the other way around. I have to go inverse warping. So I take like this and then go to this. Then I will take this h-1 to this. I will get back to this one. What is the problem with something like that? It's like not always recommended to get like the inverse of a matrix, for instance. But then one can say that, oh, maybe you will face the same things if you like to take a point and then go back to the same exact place, but this is actually will get here. So this is coming from a point that is in the middle of the pixels. Again, the same issue. But this is here differently because you are going to the inverse. And this is, if this is the case, in order to specify this, I will depend on all of the values that were here. And if I depend on all of the values that were here, I can do like an interpolation, for instance. Let's say like by linear interpolation, then I can solve something like that by interpolate the color value from the neighbors. So let's say I have these 4 points, and let's say like this is my point. We'll do by linear or do interpolation, find this point, do interpolation, find this point, then do interpolation, find this point. So this would be an easier way to get. So I have 4 points, I'm just getting the 1 point, rather than I have 1 point and then I have to get the 4 points. So this is just will be the pros and cons for that. With the inverse warping, we eliminate holes in the target image, but with the forward warping, will not require the existence of the inverse transform, if you recall. But usually the correct way is just to do the inverse warping. So just like to recall and to connect all of the couple of lectures that we had earlier to this lecture. At the very beginning, we just extract features. I have an image to the left, I have an image to the right. I'm extracting features from both of these images. Why? Because at the end, I need to see the matching, yes? I'm extracting feature from the left, I'm extracting feature from the right, and I need to connect them. I say like this corresponding to this corresponding to this, and so on and so forth. So let's say like I would detect features by anything, Harris corner as an example. And then I will use like the descriptor like sift, as we already mentioned. With this sift, we'll give like a very small feature for each particular place. And then I will do the matching. I say like, according to my descriptors, it shows that this is for instance, matches to this. This is matches to this. This is matches to this, and so on and so forth. This is matches to this. But unfortunately, with having something like that, you will get not proper matching. Yes, not proper matching. Something like out of phase. It's just, for instance, it just showed that according to my descriptor, that this little area is very close to that particular little area. So it thought that they are okay, and they thought that this matched to that. But I have to know that this is wrong. Correct? So according to whatever I have, so now I will compute the putative matches, and then I will hypothesize I transform. In our previous case, a couple of slides ago, we hypothesized that we will use the homographic, which is the projection transform with 8 degrees of freedom. You can assume whatever you would like. So I am assuming the translation and then apply to see if it is correct or not. Then I will verify the transformation, search for all the matches consistent with this particular transformation that I found. And then what else? Of course, I have to loop, and then I have just to blend the image together. Correct? But the question is, how I can, if you look at this, I have already removed the bad matches. Correct? I have removed the bad matches. I'm saying like this is matches are good, other matches are not good, and so on and so forth. How we can do that? This algorithm come to place to help us on something like that, what we called RANSAC, random sample consensus. How this particularly work? So if you recall earlier when we would like to fit a line, for instance, let's say like, okay, I will have these my lines, all of these are my what we call inliers, and these are outliers. And we showed that when we have something like that, unfortunately with the least square solution, as soon as I will find the outlier, it just like misses the direction. However, we would like actually our line to be like that. What will be the best algorithm to use? Let's say we will follow Ransack algorithm. What is this Ransack is saying? Ransack is saying, okay, so now we have these points. Sample randomly the number of points required to fit the model, assuming that you will choose your model as a line. What is the lowest number of points that you need to draw a line? Just 2. Choose these 2 randomly, and then draw the line. Okay, so I solve for the model parameter, and then using that and solve for the line. Next. After that, take a grace space that you will assume that anything within this space will be inlier, and anything outside of that space will be outlier. In this case, I just took this as this delta. This is as the delta, which means that you can approximately model that as a Gaussian noise, that the mean is equal to 0 and the standard deviation is this. And I will assume that any points located in that particular zone, I will pass. Then if you are within this zone, you pass. Within this zone, you pass. I will call you inlier. If you are outside of this zone, I will call you outlier. Then what I should do, I should count all of the inliers in this particular space that I have designed. In this case, if I do this, 1, 2, 3, 4. So the count is equal to 4. So I have 4 points. Okay, next, what I should do, choose another 2 points randomly, and then do the exact same things. Choose the delta, and then count all of the inliers. If you do this count, 1, 2, 3, 4, 5, 6. So my count is equal to 6. Then repeat. Because I already scored by the fraction, this count is 6, before it was less. Repeat this, take another 2 points, so I took the yellow points, and then draw the lines, and then do the same things with the inliers and so on and so forth. If you count this, you'll find that they are 13. Keep doing this, choose another 2 points, draw the lines, take the gracing distance, or the acceptance distance, and then count the inliers. Here you find the 19. After that, you have all of the options, which one you should pick. The one with the highest inliers. So with this case, you would pick the one with the 19 inliers. And then this will be your solution. Oh, so this is very nice idea. Just by randomly choosing this, I should be able to capture exactly what should be the correct line? Yes. And actually, it will be like more robust than the least square in terms of rejection, the outliers or the noise. Okay, so this is Ransack. We'll count like the one with the 19 and so on and so forth. So just like to recap whatever we have initial number of samples, point S, which is the minimum number needed to fit the model. And then I will have the number of samples or iterations, N, so that like as an example with probability P, at least one random sample is free from outliers. Let's say P is equal to 0.99. I will define a term called E, which is the outlier ratio, which is the number of outliers divided by the whole number of data points available, which give you a sense the percentage of my outlier. Correct? If this is high, so this means the percentage of outliers are high. If this is low, the percentage of the outliers will be low. And then I will define the distance threshold, let's say like delta, and I will choose delta so that approximately with higher probability, I will get a decent amount of inliers within my particular threshold, assuming that I have a Gaussian noise with standard deviation sigma, and it turns out with some calculation, empirical calculation, that you can get a probability of 0.95 when you choose delta square is equal to 3.84 sigma square. But now we need to calculate N. How many number of iterations or samples that I need to do in order to get the correct solution? So S, just to remind you, the number of sampled points, which is the minimum number needed to fit the model. P will be the probability of success. The percentage of E is the percentage of outlier, which is basically how many outliers corresponding to the whole data set. So if I asked you what is the percentage of the inliers, it would be just 1 minus E, correct? If E is the percentage of the outlier, what is the percentage of the inliers? 1 minus E. What is the probability of sample set with all inliers? So if it is just for one, it is 1 minus E. But if I have it for S times or S points, how many I should get? 1 minus E to the power of S. What is the probability of the sample set that one or more points will be outliers? So this guy, if I have the inliers, what will be if I have outliers? 1 minus this, correct? 1 minus that. What is the probability that the n samples will have at least one outlier? So I have this n iteration, at least one. All of this need to be to the power of n because I would expect that this is independent. Yes, and the probability of an independent variables is just not but the multiplication of the probability. Correct? Then all of these, by the way, is just equal to 1 minus p because I told you the probability of success. And here I'm telling you the probability of the outliers. So this guy is equal to the probability of the outlier, which is 1 minus p. Okay, so if this is equal to that, then I know now how to get n. Yes? You might think of this also that this should be greater or equal. You might think like if you would like to be safe, just be or less or equal than 1 minus p, sorry. Okay, so if this is the case, just do the math. You will just like take the logarithmic of this, then you will take n log this equal log this. So n will be log p over this log, as you can see here. So now I have my n, which is log 1 minus p divided by this other logarithm. So now I have the n. Let's take an example. Assuming that I have the total data points, 12 points, the minimal sample size S is equal to 2, and I have 2 outliers. What will be my E? E is the number of outliers divided by the total number of data sets, which will be 2 over 12. Correct? I have the whole 12 points. I have 2 outliers. 2 divided by 12, it is the same as 1 over 6, which is 20%. If you plug all of these values to the previous equation, you will get like n is equal to 5 to give us a 99% chance of getting a pure in linear sample. In order like to get a sense of like an acceptable consensus set, we don't have, of course, the exhaustively sample subsets of points. I don't need to take the whole n sets. Instead, I can take just n subsets, and I can do an early termination when I will terminate when my inlier ratio reaches expected ratio of inliers. For instance, I say like this is my probability of success that I would like, then I will just terminate as soon as I will arrive to that thing, just to get a sense on which parameters are affecting n the more. If you have the S with these points, if you have just two points, and assuming that I have E, the percentage of my outlier is 50%. So 50% out of my points are outliers. How many numbers of iterations I need to do in order to get to the correct line? Because this is S equal to 2, so I'm targeting a line, correct? How many times? From this table, you will find that this is equal to 17. If I have the 2 and my E is equal to 50%, I have 17. Oh, but if my model S is 8 points, how many iterations if I have a 50% outliers to get the correct answer, or a probability of 0.99 chance of getting at least one of them is correct? Oh, this is a huge number. With this Still, this is a huge number comparable to this. This is a huge number comparable to this, and so on and so forth. So you can see like S is affecting my N a lot. So then we just like plug the values, see the graphs, and so on and so forth. So just like to apply this for an image, given two images, I will have all of this corresponding. I'm saying this is corresponding to this. This is corresponding to this. This is, and so on and so forth. But from our eyes, we know that these are bad corresponding. From the greens are good corresponding, but the algorithm doesn't know that. So how the algorithm will detect this? It's exactly the same things as we did with the line. Choose one of them, and then see the correspondence. So let's say like I will take this green as the points. What is the corresponding will be the other one. So now I have two inliers, and how many outliers? 1, 2, 3, 4, 5 arrows. That is outliers. Then I choose another one and see like what will be the inliers. Now I have 1, 2, 3, 4, 5 inliers, and then 2 outliers. Which one I should choose? Which direction I should choose? Which point correspondent I should choose? I should choose with the one with the higher inliers and less outliers. So I will get the point correspondence for this, compute the H, and then count the inliers, keep the H of the largest number of inliers. So I am computing the H using all inliers, and at the same time, I am using that to solve the Ransack algorithm.